last video I was talking about how there are lots of different types of collisions. The example I gave in that one was a golf club hitting a golf ball. Well, we're going to look into a lot more detail into different types of collisions. And I want to be really clear that there are many different situations that we would consider collisions in physics. So there's the obvious, like cars colliding with each other, rugby players tackling each other, hitting balls with sticks. But there's also things like, and I've seen this one in an exam, comets or asteroids hitting planets, atoms in the air colliding with each other or with surfaces that they run into. That's pretty likely to come up in your A2 when we look more at how gases work actually. Electrons inside a current that are colliding with ions inside metal wires. That's a possible scenario that would match stuff we've been doing so far as well. We could even go as far as saying distant galaxies colliding over millions of years. So there are loads of situations where collisions are things that we would be interested in looking at. Now, there are two types of collision that I am interested in looking at. The first is what we would call a perfectly elastic collision, and this diagram shows you an example of one. So I have two trolleys here. Now they both happen to have mass m and are both travelling with the same magnitude of velocity but are in opposite directions. They then collide and are now travelling, so for both of them their direction is reversed but it still has the same magnitude. And that is an example of an elastic collision. So, just to pull some features of it out. Before the collision, I can see that object A has mass m, velocity v, so it must have momentum mv. Object B has mass m, velocity minus v, so it must have momentum minus mv. So if we just have a little look at that, then if I look at my total momentum before the collision, I have mv minus mv, so my total momentum is 0. And I could calculate my kinetic energy as well, just something else I can look at. So that gives me a half mv squared plus a half m minus v squared, which just comes out at mv squared because I can ignore the minuses. So that's the situation that's going on. After the collision, all that changed was the direction of their velocities. So if I add up their momentum, it's still going to be 0, because my first one now has minus v and my second one has v as its velocity, but that's all that's changed. So I still have momentum conserved. I also still have the same kinetic energy, because my first one is half mv squared, a half m minus v squared, but minus v squared is the same as v squared because how minuses work. I assume you knew that though. And then my second one has a half mv squared, so it comes out at mv squared. So basically what I'm saying, in an elastic collision, momentum is conserved, kinetic energy is conserved. There we go. Total energy within the system is also conserved, obviously, but we can throw that one in as an extra. So, this is an inelastic collision. Now, in this particular inelastic collision, I've got my same two trolleys, which have both got the same masses. They both have the same magnitude of velocity, but in the opposite direction. Now, this time when they collide, they both come to a stop. So let's just have a look and have a little think about what's going on here. So before, what would my total momentum be? Well, it's going to be m times v minus v times m, so 0. If I look at it afterwards, well, I have no velocity, so my momentum is 0. So in an inelastic collision, momentum is conserved. The other thing we looked at though is kinetic energy. Here, I've still got my mv squared of kinetic energy, and here I have no kinetic energy. So the feature of an inelastic collision is that kinetic energy is not conserved. Now it doesn't have to go to 0, this is just an example, but the important thing is that the kinetic energy is not conserved. Some of it gets lost as either heat or sound, most likely. So that's our big differences between our elastic and inelastic. So just to summarise for you, linear momentum is the product of mass and velocity, which we knew already. We already knew the principle of conservation of momentum, which says that for a closed system in any direction, the total momentum before is equal to the total momentum after. In all our interactions, momentum and total energy are conserved. Kinetic energy is only conserved in perfectly elastic collisions. I'm afraid I'm losing the ability to speak right now. And kinetic energy is not conserved in inelastic collisions. It can be converted to other forms of energy, so heat and sound are what they are most likely to be converted to. Now obviously, I hope we're aware that pretty much all real collisions are going to be inelastic, but as you know, sometimes we operate in magical physics land where we can sort of bend some rules in order to make the maths a little bit easier. So perfectly elastic collisions tend to be features of where we've chosen to ignore some things to make it easier. In the real world, collisions are going to be inelastic. Okay, so we will have a little look at some of these and we'll practice doing some of these calculations. If you have any questions, do not hesitate to ask when you see me.